Okay, so welcome to Math 383. What I want to do is I want to talk a little bit about some applications of complex analysis. And at the same time, there are some topics which you should have seen in your education in mathematics before here. And so I will just review these things, but you have clearly seen and clearly understood beautifully. So it'll just be a refresher on things that have been covered in previous classes. All right, so we're going to talk about eigenvalues of matrices, and then we're going to go from that into random matrix theory and L functions. Yeah, I could give an entire semester, course on either half of the second bullet point. So this will just be a 1, maybe 2-day introduction to the topic. For those of you who are not graduating and are interested, I will be looking at questions related to this in small 2022. So if anybody's interested, happy to talk more about that. If you are going to graduate but are interested in doing something like this, it's a little bit harder, but still talk to me because there are some things that possibly can be done. I am including a link, and I'll try to remember to just email this to you directly as well, a beautiful paper by Nobel laureate Eugene Wigner on the unreasonable effectiveness of mathematics in the natural sciences. So I can see at least two people shaking their heads, that they have read this. It is absolutely amazing how many diverse systems can be modeled by the same mathematics. And once you can do the mathematics, you can do basically a search and replace. I'm going to replace mass with charge. I'm going in. All of a sudden, you have very similar results. So it's worth reading this article. All right. So I spent a little bit of time this morning just quickly jotting down some basic facts about matrices. So we say A is symmetric if A equals A transpose. Normally, when we talk about a symmetric matrix, we assume the matrix is real valued. But we just mean A equals its transpose. A matrix is complex summation if it equals the complex conjugate transpose. So you take the complex conjugate of all the entries, and then you take the transpose of that. We often use the capital letter H to denote the complex conjugate transpose. And so, for example, the matrix 3, 4, 4, 2 would be a real symmetric matrix. 3, 4 plus I, 4 minus I, 2 would be complex summation. You should be able to show quite straightforwardly that if you're complex summation, the diagonals have to be real valued. Okay. Next, if I give you a vector in Cn, then the length squared is just V Hermitian H, the complex conjugate transpose of V with V. It's not V dot V. And so, for example, if I take the vector 1, comma I, and I just do V transpose V, which is V dot V, you would get 1 squared plus I squared, which is 0. And the only vector that should have 0 length is the 0 vector. So this tells us that just taking the dot product of a vector with itself is not going to work. We want to do the complex conjugate transpose. We saw this when we talked about the inner product when we were looking at Fourier analysis, that if we wanted to do the dot product of f and g, it was the integral of f g bar. Okay. So next is the eigenvalues and eigenvectors of a real matrix are not necessarily real. So we've talked a little bit about this throughout the semester, and this is one of the reasons why I like giving lectures like this as we wind down. It's a nice way to review everything we've done. If I give you a polynomial with integer coefficients, does it have to have integer roots? No. So I could give you, 3x minus 2 equals 0, so x equals 2/3. Okay. If I have rational coefficients, does it have to have rational roots? No. All right. If it has real coefficients, does it have to have? No. If it has complex coefficients, yes. And that's where it gets amazing. Once you introduce the square root of -1, you don't need anything else. And the process just stops and you have what's called algebraically closed. So it's always interesting to look at where is the space where the solutions live. So I can give you a real matrix where the eigenvalues and the eigenvectors are not necessarily real. And the simplest one that I can think of is a rotation matrix. So the rotation matrix rotates you by theta radians if you're a mathematician, or rotates the coordinate axes by theta radians if you're a physicist. I think this is how it's done. That there's a dispute as to, are you changing the object, or are you changing the axes? And it can change where you put the minus sign. So has anybody here seen this written with the minus sign in 2 different places? Yes, and so you have to be careful as to which source are you using, and are they viewing it as rotating the point, or are they doing it as rotating the coordinate axis? So if I take a vector v and I rotate it by theta radians, well, what does it mean to be an eigenvector? It means when you act on it by the matrix, you have the same direction, you just rescale the magnitude. Given that the rotation matrix physically rotates the direction, as long as I don't rotate by 180 degrees, it's going to be a different direction and it can't be an eigenvector. So as an exercise, you can then try to figure out, well, what would be the eigenvalues and eigenvectors of this matrix? It can't be anything that's real. So it's going to have to somehow be something complex. Okay, so one of the big theorems is if your matrix is complex Hermitian, then the eigenvalues are real. What is lurking in the background here is eventually often done in linear algebras like the principal axis theorem. If I give you a real symmetric matrix, any real symmetric matrix has an orthonormal basis of eigenvectors. Does this sound vaguely familiar?
Yes, but we don't cover it.
Okay, I was about to say, I might even have a pin that I could just drop when I ask a question like that. Okay, so this is one of the gems of linear algebra. So in general, if I am trying to understand the effect of a transformation, it would be nice if the transformation could be written in a diagonal form. Because then it's very easy to look at not just the matrix, but also high powers of the matrix. Again, there's a lot of great quotes on this. When you write a matrix down, you have to choose a basis. So the whole point of linear algebra, at least one of the big points of linear algebra, is depending on the problem that you're looking at, you want to choose a basis that makes computations convenient. And there's a lot of great quotes about, you never ever actually write anything down and do computations in public. You do it privately, you work in abstract theoretical nonsense. But if you actually want to do a calculation, you want to choose a coordinate system that is nice. So I think we've talked about, the equation of an ellipse. If the ellipse is aligned with the coordinate axes, it's easy. It's x over a squared plus y over b squared equals 1. If it's not, we use the rotation matrix we had a moment ago to rotate the coordinate axes to align with the ellipse. Then we write down the equation of the ellipse in those coordinate axes, and then we undo. And so the whole point of linear algebra is if I have an orthonormal basis of eigenvectors, a bunch of perpendicular, mutually perpendicular directions, then I write a general vector as a linear combination of these. And if I apply a n times, I would just get c1 lambda 1 to the n v1 plus c2 lambda 2 to the n v2 and so on. So it makes it very easy to understand the effect of matrices on general vectors if I can have a nice orthonormal basis of eigenvectors. And so the question is, when do you have such? Not every matrix has an orthonormal basis of eigenvectors. Does anybody remember enough linear algebra to give me a matrix that does not have an orthonormal basis of eigenvectors? I'm sorry? Well, will not be a Hermitian matrix. Hermitian matrices will have an orthonormal basis of eigenvectors. Do you remember how many people did Gauss-Jordan forms? Doesn't get done here. Non-diagonalizable matrices. So 0, 1, 0, 0. So that would be a good example. It has a double eigenvalue of 0, but it only has one eigenvector of 0. You don't have enough directions. It turns out if your matrix is n by n and it has n distinct eigenvalues, then it will have n eigenvectors. They may not be mutually perpendicular, but you will at least have a basis of eigenvectors. So the trouble is when you have repeated eigenvalues. Part of what I'm doing is I just want to put some things on your radar. It's not going to be on the tests, it's not going to be on the exams, but you should at least know stuff like this exists. On a lot of qualifying exams, they love to ask questions about Gauss-Jordan form. So if you've never seen what Gauss-Jordan form is, Jordan canonical form. If you've never seen Jordan canonical form, write that down, Google it later today, and just be aware of its existence. Frequently, you can't always get things to the form you want, so you ask, what is the best form I can get something to? The best form that you can get for every matrix is Jordan canonical form. But there are other forms that you can get if your matrix has a few additional nice properties. One particularly nice property is being Hermitian. So if A equals AH, the complex conjugate transpose, then it turns out that all of your eigenvalues are real. And so I'll first prove this, and then I'll explain why we care so much about this. So the proof is to consider V Hermitian AV. And we use the associativity property. It's kind of nice that we finally use things like associativity after talking about it for all these years and making sure we know about it. Well, I can have A acting on V and then act on it with VH, or I can have VH acting on A and then act on that by V. So let's put the parentheses in the two different ways. And because A is Hermitian, I can replace A with A Hermitian on the left, and then V Hermitian, A Hermitian is just the Hermitian of A times V. And again, we're using very similar, if you have the transpose of a product, it's the product of the transposes in reverse order. And complex conjugation of a product is just the product of the complex conjugations. Well, because V is an eigenvalue, V is an eigenvector of A with eigenvalue lambda, then AV is just lambda V. And whoops, the Hermitian should be outside the whole thing. I apologize. But we should have a Hermitian over the lambda over there. And so when we pull this out, we get a lambda bar V Hermitian V. On the other side, when we look at what's going on, what do we have? Well, A acting on V just gives us lambda V. There's no Hermitian, so we can just pull it out. And because V is not the zero vector, V Hermitian V is not zero. So we can divide both sides by that. So we get lambda bar equals lambda, which means lambda is real. So the eigenvalues of Hermitian matrices are real. Why is this important? Well, in physics, we like to talk about energy levels. And your energy levels are going to be real valued. You have spacings. You can talk about what's the next energy level. I think one of the earliest extra credit assignments in this class was to prove that you don't have a well ordering on the complex numbers, that you can't talk about which one is next. And so it's really nice that we have a ordering over here. And the hope is that for certain systems, we can have a correspondence with some physical systems and some number theoretic systems. These might be good models. The most general type of matrix that people look at to get theorems about the like the principal axis theorem would be normal matrices. Out of curiosity, has anybody done normal matrices? That's where you commute with your complex conjugate transpose. Okay. So a corollary is the eigenvalues of real symmetric matrices are real because a real symmetric matrix is just a complex Hermitian matrix with real entries. So, if you're a real matrix and you're symmetric, you're trivially Hermitian. So we talked about why this is important. We can order things, thinking of energy levels. And then one can ask, are there other types of matrices that have nice properties? And by nice properties, I mean, I want nice properties of the eigenvalues. So for the complex Hermitian matrices, the eigenvalues lie along a line, they lie along a one-dimensional space or curve. Does anybody know any other family of matrices where the eigenvalues have a nice property? The orthogonal matrix, and more general than orthogonal, orthogonal is a special case, it's the real example. Unitary. So how many people have seen unitary matrices? So this is a little bit of a linear algebra introduction. So a unitary matrix is a matrix such that U Hermitian U equals U Hermitian equals the identity. The real analog is the matrix Q is orthogonal if Q transpose Q is Q transpose is the identity. And the way you should think about this, for the orthogonal matrix, let's think about the orthogonal matrix. This basically means the ith row dotted with the jth row is 1 if I equals j and 0 otherwise. Oh, so if I take the dot product of a row with itself, I get 1. That means it has unit length. And if I take the dot product of it with another row, I get 0. That means it's perpendicular. So an orthogonal matrix is just a collection of n unit vectors that are mutually perpendicular. And the unitary matrix is the generalization of this. So these matrices occur all the times in mathematics and physics. They're well worth understanding and knowing. So they have a lot of special properties. One of them is the eigenvalues of unitary matrices can be written in the form e to the I theta, where theta is a real parameter. So to see that this is true, we do a very similar trick. The difference now is before we looked at V Hermitian AV. Now we're going to look at essentially V Hermitian U Hermitian UV. And why are we looking at U Hermitian U? Well, because U Hermitian U is the identity. So whenever you're doing these arguments, you always want to ask, how can I use what I'm given? I'm given the identity. So if I shove the identity in between, I don't change anything. In the previous one, I had A equals A Hermitian. So I can start off with just A by itself. and replace A with A Hermitian. Now, I don't have anything nice by U to U Hermitian. I only have something nice involving their product. So this is a very natural thing to look at. So if I look at the length of V squared, it's V Hermitian V, which is the same as V Hermitian U V, because U Hermitian U is the identity. Well, V Hermitian U Hermitian is just the Hermitian of UV. And the U acting on V, because V is an eigenvector with eigenvalue lambda, is going to be lambda bar. Similarly, U acting on V is just going to be lambda V. And so we get lambda bar lambda V Hermitian V. And that has to be equal to the length of V squared. Well, since V is non-zero, its length squared is not zero, so I can divide. So I get lambda bar lambda or lambda squared equals 1. So that means I have a number of absolute value 1. If I have a number of absolute value 1, I can write it as e to the I theta. So the eigenvalues of unitary matrices can be represented by a real parameter. So they lie on the unit circle, and you can talk about the spacings between eigenvalues. Really, instead of saying eigenvalues, what would you say? Eigenangles, right? Anybody know what eigen means? Sorry?
Property of something.
Property of something.
Like own, mine.
Own, yes. Were you going to say the same word, or? So I think I remarked that, when I was first learning them, I thought eigen was the name of the mathematician. And eigen was extremely prolific, up there with Rita in terms of just sheer volume of work done. But this tells us that these are going to be a nice space of matrices to look at because their eigenvalues have wonderful properties. So we've talked a little bit about the eigenvalue trace lemma. And so it's so important, I just want to mention it again. So the trace of A is the sum of the diagonal entries. And the trace of A turns out to be the same as the sum of the eigenvalues of the matrix. If you don't know how to prove this, I strongly urge you to try to fill in the details of the proof sketch. The idea for the proof sketch is to start off with a very easy case and build up from that. The easiest case is when the matrix is diagonal. So why is this an easy case? Yeah, if you're a diagonal matrix, then your eigenvalues are just the diagonal entries. And the sum of the eigenvalues is then going to be the same as the sum of the diagonal. So it's trivial if your matrix is diagonal. So sometimes you start off with a simple case and try to build from that. And then you can say, well, how can I tweak a diagonal matrix and still be doable? Well, I want the eigenvalues to be the diagonal entries. So when are the eigenvalues of a matrix equal to the diagonal entries? If my matrix is upper or lower triangular, then the eigenvalues are still going to be the diagonal entries. And so any upper or lower triangular matrix works. Any econ people here? Anybody take an econ class? Okay. I'm thinking of the most famous curve in economics. What curve am I thinking of? I'm gambling here that you're going to say what I'm thinking of. Yeah, supply demand curve. Which axis is quantity, which axis is price? And could you do it the other way? Yes. Does it make any difference? No. If you did it the other way, the economists who are already confused enough with some of the mathematics, it would be terrible, right? It could be disastrous, right? But could you switch it? Without a doubt, it makes no difference. Could we work with lower triangular matrices other than upper triangular? Yes. The convention seems to always be to move things into upper triangular form. Doesn't really matter. If our matrix is upper triangular, it's not a problem. And a nice exercise is to show that you can always find an invertible matrix S such that S inverse AS is equal to T. And so it's a nice exercise, prove that you can do that. And the hint is to try to do it by induction, is slowly move your matrix into upper triangular form piece by piece by piece. And the reason this is useful is the trace of a product has this nice cyclic property. So the trace of ABC is the same as the trace of BCA. So the trace of S inverse AS is the trace of AS S inverse, which is then just the trace of A because SS inverse is the identity. So this is a sketch of the proof of the eigenvalue trace. Okay, so why do we care about stuff like this? Well, frequently we want to understand the eigenvalues of a matrix. As you probably learned this semester, I have some strong views. I think it is a crime to leave a linear algebra class believing that the following is how you calculate eigenvalues. So how do you calculate eigenvalues? What do you do? Characteristic polynomial, determinant of A minus lambda I, right? So if you have a 10,000 by 10,000 matrix, good luck trying to do this, using characteristic polynomials. We are not going to solve a 10,000 degree polynomial. So there are some incredibly powerful techniques to approximate these solutions, to approximate the eigenvalues. And it's a really interesting question to try to figure out just what it is. The way the method of moments works is the following. So imagine we have the eigenvalues lambda 1 through lambda n, and we're going to look at the mth moment, which is the sum of the eigenvalues to the mth power, and then we divide by 1 over n because we have n eigenvalues. So you can view this as putting a massive size 1 over n at each eigenvalue. And the idea is, if we know the eigenvalues, do we know the moments? Yes or no? What do you think? Yeah, I mean, the moments are defined as sums of the eigenvalues to powers. So if we know the eigenvalues, we clearly know the moments. What about the other direction? If we know the first capital N moments, should we know the eigenvalues? Should it be able to go in both directions? We essentially have a system of big N unknowns, but we have big N equations. So the hope is that if you know the moments, you actually know the eigenvalues. The problem is taking the limit as the number of eigenvalues goes to infinity, as the size of the matrix goes to infinity. Then you can have situations where it's not enough to know all the moments. And we've talked a little bit about this problem before in complex analysis, that you can have two probability distributions that have the same integer moments but are not the same. And there are ways around this, but the general idea is that if things are nice, if you know the moments, that should give you some information about the eigenvalues. It is hard to work with the eigenvalues of a matrix. We don't want to calculate the characteristic polynomial. But calculating trace is very easy. And the trace of a squared, a cubed, a, these are just polynomials in the matrix entries. So the hope, and this is the field of random matrix theory, is that by understanding the matrix elements, you then understand the eigenvalues. This should remind you of something we've seen in number theory in this class. And somebody will have to email this to Ben. So what does this remind you of? We know one object and we use that to get information about another. We've seen something in this semester where we can pass from knowledge of sum of a one object to a sum of another object. I'm sorry? Yes, say it louder. Sure. I mean, I would just say the primes. We have the Riemann zeta function, which relates a sum over integers to sum over primes. The integers are quite well understood, right? I think I've told you we even have an explicit formula for the nth integer. So the hope is that by understanding the integers, you can pass from that to knowledge of the primes. It's the same thing here. The hope is that by understanding the matrix elements, we can pass to knowledge of the eigenvalues. Okay, so what I want to do now is I want to transition to a technical talk about actually trying to apply this. So I am probably one of the last people to start off working in nuclear physics and migrate over to number theory. So my mentor when I was an undergraduate was one of the original experimentalists who worked in the 1950s and 1960s in gathering data of the internal structure of heavy nuclei. And if you're lucky, you have on the order of 1,000 data points, and you're often not lucky. And when he found out that, wait, you can get billions of zeros of the Riemann zeta function, without too much work, the ability to look at such large data sets was phenomenal. And so the subject really took off in the 1970s when Montgomery was a graduate student and he was looking at properties of pairs of zeros of the Riemann zeta function. And he was visiting the Institute for Advanced Study, and he was talking to the great mathematical physicist Freeman Dyson. And Dyson was always encouraging of young people and wanted to know, what are you looking at? And when he showed it to him and said, this is the result I get looking at the zeros, oh, that's amazing. We see something very similar in random matrix theory when we look at the energy level of heavy nuclei. And so this is one of the best examples in science of why you talk to people, because you can make strange connections. It's like, wait a minute, I've seen this someplace else. And this is why I have the Wigner paper referenced, as to why do you see the same stuff in so many different places? The same mathematics that models the zeros, the Riemann zeta function, models the energy levels of heavy nuclei, models the eigenvalues of matrices, it applies in so many different places. If you want at a truly fundamental level, think almost like there's a central limit theorem lurking in the background, and that's what's responsible for the universality. If you're going to graduate school, you have two types of projects you can work on. You can work on the brick and mortar, the pretty standard, the theory's already there, I'm going to get the next brick, and you can work on the broad, new advances, new areas. It's dangerous to do nothing but big projects, because if they don't work out, you have nothing. And you want to try to find a nice balance between the two. It's important to know what are the big questions, what are people looking at? And when you are trained in one area but can talk to people in another and find out what they're doing, you have the opportunity to make some real progress. And so these connections between number theory and physics were phenomenal. And it turned out you could actually use each subject to predict a bit of what the other would see. The techniques and the methods of proof are completely different, but you have similar behavior in the end. All right, so I will talk a little bit about how to look at some problems and what to look at. I will eventually try to explain how to view nuclear physics from a number theory perspective or number theory from a nuclear physics perspective. And so that will be even worse than a Boston accent masked with something like this. So there's a couple of general questions in all problems like this. The first is you have to determine the correct scale to study things at. We've talked a little bit about the central limit theorem, where we talk about subtracting the mean and dividing by the standard deviation, standardizing to having something that has mean 0, variance 1. So you want to figure out what is the right scale. We've also seen this recently when we were doing Stirling's formula and we were doing the stationary phase Laplace's method, where we looked at the integral and we said, okay, let's look at the integrand. Where's the integrand largest? Let's see how far we can move. It was all about trying to find what was the correct scale. And this is one of the key ideas. And again, my goal for the last few classes is to really drive home what you've done, not the specific facts, but the general techniques. And one of the big techniques of this course is trying to find what is the right scale to study things at. The next, as I mentioned, is we see similar behavior in different systems, which is extremely exciting. Sometimes it's only the main terms that are the same. And at the lower order terms, that's where the arithmetic or whatever your field specific stuff lives. And then I'm going to try to discuss a bit of the tools and techniques needed to prove the results. And then my general advice is to try to find subsystems with interesting behavior. So as you get further and further in advanced mathematics, it becomes harder and harder to do calculations. And what you can do is you can no longer say, I can no longer really calculate anything exactly. What I can do is I can put it in a family and I can somehow average over the family and calculate what's happening on average. And maybe if I'm lucky, I can maybe calculate a standard deviation as well and say how close most things are to the average. So the idea of being able to do a specific calculation, it's just not going to happen. But you can often do averages. Well, the more things you average over, the easier it's going to be to do the calculation, but the more likely it is that any interesting behavior is going to be washed away. So if you look at averages of math ability of people in this classroom, do you think this is representative of Williams in general? No. And if you look at math ability at Williams, do you think this is representative of American institutions in general? No. So the bigger you have, the more likely key things are going to be washed away. So what you want to do is you want to look at the smallest set you can, where you can still actually execute the calculations. We can actually do the summations and find what the limits are. All right, so the general formulation is we have some system and we observe values at T1, T2, T3, and we want to understand what rule governs the spacings. So every now and then we reach a point where the age difference really matters. Did I mention the Macarena in this class, or was it in probability? I did in this class, right? This is one of the ones where it actually matters that my wife is 2 years younger than I am, because it was high school for her, it was college for me. How many people have ever been in a bank? Okay. How many people have gone to a bank where they have multiple lines and you wait in multiple lines? Most of the time when you go to a bank, how does it work? I'm sorry, ATM. Is there just one ATM or are there multiple ATMs? Do you wait behind each or in front of each ATM? Does each ATM have their own line, or is there one line and then you just go to the next available? Are we? Not very. Society as a whole, even less. But typically, do you have one line feeding into and you just go to next open, or does each one have their own? Supermarkets, you have your own line. But in banks, it's usually there's one line and you just go to the next available. ATMs, next available. If you're buying Metro cards for subways, it's often just you go to the next available machine. Why? It's the same average wait time. Not a bad guess.
One seems more democratic.
One seems more democratic. Yes. Good. The variance of wait time is smaller when you have one big line. How many people have ever seen When Harry Met Sally? Yeah, I figured. All right, so they talk about high maintenance people. And so you could have somebody who is extremely high maintenance who's going to knock a teller out and have all these special requests, and I want all these crisp bills for holiday cards and everything like that. And you get stuck behind them and you just get so frustrated while the other line is just whipping through and you curse yourself for the rest of the day. I chose poorly. If you have one line, then if you have somebody who's high maintenance, they're not knocking out everybody behind them in that teller. They're just knocking out that teller. And so the average wait time is the same, but the variance is going to be much better in a situation like this. And you're less likely to have somebody who's very frustrated. A place that really cares about trying to study the distribution of something like this is Disneyland or amusement parks. They are phenomenal at understanding wait times and how long do you have to wait before something happens. So there's lots of different systems you can study. I'm not going to put something up like Disney because I'm a mathematician, I do the theoretical stuff, but you could apply it in a setting like that. I'm going to care about things like energy levels of nuclei, matrices, zeros of L functions, lots of things like that. And so for the most part today, we're going to talk about the first three. And so there's 3 steps in all the proof. The first, as I've mentioned before, is you have to find the correct scale to look at things. The second is you need some kind of explicit formula relating what you want to study to what we can study. We've already seen that with the Riemann zeta function, representing sums over primes to sums over, products over primes to sums over integers. The eigenvalue trace lemma is the prototypical example relating these sums over matrix elements to eigenvalues. And then the last is these explicit formulas would be useless if we couldn't actually do the sums that arise. So you need to be able to have some kind of averaging formula to execute at the end of the day the quantities that you want to study. All right, so this is only a subset of people that I have worked with on problems like this over the years. I'm going to talk a little bit about classical random matrix theory. So who are my physicists again? All right. Have you studied the 3-body problem? So if you have a universe with 1-point mass and nothing else, it's really not that hard to write down physics. 2-point masses and nothing else, it's still not that bad. We can write it down in closed form. 3-point masses in general configuration, no, it's not by induction, everything is easy. 3-point masses in general configuration, we can't write down a closed form solution. It is not entirely clear what's going to happen to the orbits of the planets. Whether or not something keeps the labeled planet, that's a human question. The actual orbit, completely different. Now, you can sometimes prove theorems such as, the planet maybe stays in a bounded region, but we can't write down a closed form expression for where it will be. If we can't do 3-point masses under gravity in general configuration, imagine something like heavy nuclei, like uranium, where you have over 200 protons and neutrons with a far worse force. And so it's absolutely hopeless to try to write down what's going on. In your physics classes, have you done hydrogen? Yay. Okay. So what's the system for hydrogen that you study? One proton and one electron. Did you do helium? I'm sorry? Excellent. 2 protons, 2 neutrons. Okay. Did you go beyond helium? No. So, but in terms of just how far we've gone, in terms of being able to write things down, we don't get that far. So the idea, and I love this, is the way you understand what's going on inside a nucleus is you shoot some high energy neutrons and you see what comes out. So the best quote I ever heard is, imagine you want to understand the workings of a grandfather clock. So you take 2 grandfather clocks, you accelerate them to 0.99 the speed of light, smash them together, look at all the cogs and gears that come flying out, or the pieces of them, because they're not going to come out fully formed. And from that, you try to deduce the internal workings of a grandfather clock. This is subatomic physics. And it turns out in number theory, there is the equivalent option to do something like this. There are analogs of neutrons, there are analogs of shooting things into heavy nuclei. And we'll talk about that probably in the next lecture. So the general idea in quantum mechanics is you have this matrix H, the Hamiltonian, the Cn are the energy eigenfunctions, the En are the energy eigenvalues. There are 2 reasons why this is not studied in a standard linear algebra class. The first is H is infinite by infinite, and I believe for the most part you only look at finite by finite, correct? And the second is we don't know any of the entries of H. So it's kind of hard to diagonalize an infinite by infinite matrix when you don't know any of the entries. So Victor's great insight was basically to say, screw that. Let me look at very large n by n matrices, understand what's going on, and I'm going to just keep sampling from the space of n by n matrices. And the more matrices I sample from, this should give me a sense of the average, and then I will pray that some kind of central limit theorem kicks in, and that most systems are close to the average. So in a simple case, imagine you have all molecules are moving at the same speed, and they're moving either left or right. And you want to calculate a quantity such as pressure. So you need to know how many molecules hit a wall at a certain amount of time. But what you can do is you can look at every possible configuration of air molecules in the room. For each configuration, you calculate what the pressure is, then you average, and it should be a pretty good approximation for most systems. Is it possible that all the air molecules are in my half of the room? Yes, unlikely though. And so if you have n molecules, you would expect about n over 2 in each half of the room, and you would expect fluctuations to be of size square root of n. Anybody want to tell me roughly how many molecules are in the room? Within, say, 3 orders of magnitude. Yeah, I was going to say 10 to the 26. Avogadro is around 6 times 10 to the 23. So put in a factor of 1,000 for here. So we have on the order of 10 to the 26 molecules in this room. The square root of n divided by n, that's 1 over 10 to the 13. That's an extremely small error. We're not going to really detect this. And so a lot of things are going to be very close to the average. And what Victor's great insight is that you could model nuclear physics this way. And so for instance, let's take a real symmetric matrix A, so A transpose equals A, and then we'll say the probability of a matrix is the product of the probability of the independent entries. So since it's real symmetric, if I know the upper triangular part, I know the lower. Or more explicitly, the probability that I have a matrix where Aij is in the subinterval is just the product of the integrals. And then what we'll do is we'll take delta to be the Dirac delta functional. If you want, this is the limit of our approximation to the identities. All the mass is concentrated at the point x naught. And so if we integrate f against delta, it just returns the value of f at x naught. And so if I want to understand my matrix, I put a mass of size 1 over n at each of the normalized eigenvalues. And when I'm trying to normalize the eigenvalues, I'm dividing by 2 square roots of n. Which do you think matters more, the 2 or the root n? Yeah, the root n. The root n is telling me how the eigenvalues of the matrix grow with the size of the matrix. The 2 is just so I can say circle rather than ellipse later. And if I want to count how many normalized eigenvalues are in an interval a to b, well, I just integrate from a to b, and that will just give me the count. And so if I want to calculate the kth moment, I would just, instead of integrating 1, I would integrate x to the k. And instead of just counting 1 every time, I would count lambda to the k. And so the first big result in the subject is Wigner's semicircle law, which says that if you look at n by n real symmetric matrices, if you choose the entries independently from a fixed distribution with mean 0 variance 1 and other moments finite, and this can be weakened a bit, then these count measures converge to a semicircle. And so the proof of this is using the eigenvalue trace lemma. And so if I want to calculate the moments, well, the kth moment is the trace of a to the k. A to the k is a polynomial. It's a polynomial in the matrix elements. So what I can do is I can just put that into the calculations. Now I divided by square root of n. Where did that square root of n come from? Well, the trace of a squared is the sum of the eigenvalues squared. So when I expand out the trace, I have the sum of aij squared. These are all drawn from a distribution with mean 0 variance 1. So these are all of size 1. I have n squared terms, so this sum is of size n squared. So the sum of the squares of the eigenvalues is of size n squared. So that means each eigenvalue, since I have n of them, should be roughly of size square root of n. And this gives you an idea, heuristically, what is the correct scale to study things. And then if we want to calculate the kth moment, well, we have the trace of a to the k. That's the sum of the eigenvalues to the kth power. This is just a polynomial in the matrix elements. I then weigh it by the probability I chose that matrix, and I somehow have to do these calculations. And if I can do these calculations, then all of a sudden, I'm in business. So these calculations require a lot of different subtlety. They require tools in a variety of subjects, a lot of combinatorics, a lot of integration theory, but also occasionally complex analysis. And so what I want to do for the remaining time today is talk a little bit about the complex analysis. So I will ignore, for the most part, the combinatorics, which is interesting. Now, if I have something like this, I'm choosing my entries to be from a distribution with mean 0 variance 1. If any of these a's is not matched with another a, when I integrate, what will I get? So if I ever have an a that's unmatched, what would I get when I integrate? 0, because each a has mean 0 variance 1. So every a has to be matched in at least pairs. Every aij has to be matched with another one, or the contribution is going to be 0. Could I have something matched as a triple? Yes. Or a quadruple? Yes. And then what you do is what one of my advisors said you do, you're counting on fingers. We're dividing by a certain power of n. It turns out if anything is ever matched in a triple or quadruple, that when you count how many such tuples there can be, it's going to be a power of n smaller than k halves plus 1. And because we're assuming all the moments are finite, when we divide by n to the k halves plus 1, it's going to give a 0 contribution. So the only thing that survives are when the a's are matched exactly in pairs. So no triples allowed anywhere. And then the question becomes, how can you match them? And this is where, depending on which family of matrices you look at, you will see different behavior. So the most interesting ones are to impose some structure on your matrix. The weakest structure is to just say, I have a real symmetric matrix. If you've seen the Catalan numbers, it's the Catalan numbers that emerge when you look at the real symmetric matrices. How many of you have never heard of Catalan numbers? Okay, there's a lot of places where the Catalan numbers occur. One of them is if I give you a string of left and right parentheses, where you have as many left parentheses as right parentheses. As I go through, as I'm walking, I can never have seen more right parentheses than left parentheses if I want it to be legal. So the number of ways to put them down is equivalent to one of the definitions of the Catalan numbers. Another one is if I want to walk from the bottom left to the upper right on a square, and I can only move one step east or one step north, and I have to stay on or below the main diagonal, that's equivalent to the Catalan numbers. And you can see the analog between left parentheses, right parentheses. The Catalan numbers, yet again, Wigner, these occur in so many different areas. Depending on what matrix ensemble you look at, you will see different structures. So I will end with some pictures, and then I will end after that with what we'll talk about on Monday. So here's a plot from 500 Gaussian matrices, 400 by 400. If you have really good eyesight, you might be able to see that there is a red line. This is the semicircle. And this is just showing that the distribution of the normalized eigenvalues is looking like the semicircle. Can anybody give me a probability distribution that does not have finite mean, finite variance, finite higher moments? Cauchy. So we could ask, what happens if we put the Cauchy in? Very different. Now, it's not an unexpected spike over here. This is just everything from 300 onward. You see very different behavior in the Cauchy, but there is a way to make something like this work out. And so I will leave a link to that. So what we will talk about on Monday is block circulant ensembles. One of the people here, Murat, was an undergraduate at Williams. At the time, he worked on me on smallness, and he did not know complex analysis, but he needed to know complex analysis for this project. So he got the 1-hour version of this class. Just what do you need to be able to do a contour integral? And we will see on Monday how a contour integral arises in studying this family of matrices. So this is going to be symmetric matrices where the diagonals are periodic and they wrap around. So C2, D2, C2, D2, C2, D2, and then it wraps around like this. The advantage of having them wrap around is now each diagonal has the same length. Otherwise, different diagonals would have different lengths. The main diagonal would be the largest, the one in the corner would be the smallest. And we will see when we study this that this is going to be related to complex analysis. It's going to be related to algebraic topology, going to be related to advanced combinatorics. So there's a lot of good stuff to be seen from here. And again, the goal is to just show you applications of what we've been doing all semester. All right, so this is a good place to stop.